Fundamentals of ECG. The first part of three. This is electro. What is ECG or electrocardiogram? ECG or EKG is a test that checks for problems with the electrical activity of the heart. However, we want to evaluate the heart function. But make a note, electric activity is not equal with the mechanical function of the heart. An ECG shows the heart electrical activity as line tracings on paper. The spikes and dips in the tracings are called waves. The dipole model of the heart. When we do have the smooth muscle cells, they're attached to each other. Inside they do have more negativity. The membrane potential of the muscle cells around minus 90 millivolt at rest. When we depolarize this resting cell, the fast sodium channels are opening up and sodium flows in. Immediately in this depolarized area, outside be more negative comparing to the other cells that is not depolarized yet. When this depolarization spreaded along, as you see here, this depolarization vector pointing toward the undepolarized area. If you place an electrode at this point when the cells are not depolarized yet, we are going to record a positive deflection, a positive potential differences. As long as the cells are not depolarized fully, we are going to detect positivity, and when they depolarized, basically we do have an isoelectric line. The repolarization usually starting where the depolarization started. However, because we do have different charges going on, so now the depolarized area relatively be more negative inside and outside. This is why this vector is going to point the opposite way. So during the repolarization, we do have a negative deflection. This kind of model is a bipole model. The dipole meaning that we do have a positive and negative charges separately. They are not falling in the same portion. This dipole can be substituted with a vector, the vector that has a direction and has a size. This dipole is going to generate an electric field, and between these two fields we can measure the potential differences. We are going to record the highest difference when we are going to put the voltage meter in the center of this dipole, and when we are parallel with this vector. And of course, when we are perpendicular, because the electric field has the same kind of charges, we do not record anything. So the potential differences that can be recorded in this electric field is going to depend or going to be proportional to the axis that the dipole and the measurement of the electric field axis is going to close each other, the cosinus alpha of this axis. Very similarly to this dipole model, the heart electric activity can be modeled as well, and we can use these vectors as a dipole when the heart is going to depolarize. The depolarization and the repolarization of the ventricle. The depolarization of the ventricle is started in the endocardium and goes toward to the epicardium. And when we place an electrode on the surface of the epicardium, we are going to record a very narrow and very fast positive deflection. The repolarization is opposite of the before I started to say about it. So it's not cell-to-cell repolarization going on, and the repolarization doesn't go from the endo to the epicardium, But in a normal heart, it's going and started the repolarization in the epicardium and goes toward the endocardium. The reason, if you are looking at the action potential of the muscle that is obtained from the endocardium, they do have a much wider and much longer plateau phase comparing to the epicardium. So this is why this contraction or the depolarization ending first in the epicardium, and this is why the repolarization exactly be the opposite. However, because different charges are going on, so replacing not negativity and positivity, now we are going to detect a positive deflection. ECG cannot be used for everything. We have to know the advantage and the disadvantage of the ECG. The advantages is, for example, the non-invasive examination doesn't hurt. It is fast and widely available. Fast means that you can have immediately the results, the test results. You don't need to wait for taking the samples to the lab and waiting for the results. The registration can be made inexpensively. A paper or connected to the computer relatively is cheap. In many cases, the diagnostic accuracy is good, but not all the case. The disadvantages is not providing direct information about the heart function, needing expertise, not so cheap to train a physician. Many times, only the suspicion of the pathological conduction can be detected, and we have to use different tests to be sure that the heart is suffering of the pathological condition. This table is going to summarize the diagnostic precision and accuracy and informative values. As you see here, the ECG can be used very well to diagnose arrhythmias, ischemic heart diseases, myocardial infarction, and barely can be used, for example, to detect any kind of valve abnormalities, cardiomyopathies, developmental abnormalities, emphysema, pulmonary embolism, or ion changes. However, we do have some sign on ECG, but we have to use different tests to prove our diagnosis. Hypertrophy and pericarditis, again, they do have some sign on ECG, but not as accurate some and other tests. Anatomy of the intrinsic conduction system. Every impulse normally made by the sinoatrial node. This is a pacemaker center that generates the impulse. This impulse is spreaded to the atrium. They do have some kind of internodal pathways that directly connected to the AV node that is located between the atrium and the ventricle. The AV, the atrioventricular node, again, they do have a pacemaker capability. However, the on rate is less comparing to the sinoatrial node. In the AV junction, the, uh, the depolarization wave going slower comparing to the muscle, and they have a little delay before they enter into the ventricle. The bundle of his that is going to go through to the endless fibrosis and is divided into the bundle of branches, and the bundle of branches is ended in the Purkinje fibers that is going to synchronize or connecting to the ventricular muscle cells. So when the charge comes to the bundle of branches, very fast spread it and very fast causing a synchronized depolarization of the ventricular muscle. The action potential of this nodal tissue. The nodal tissue, they do not have a resting potential. They do have a continuous sodium flow. This is the funny sodium current that is going to depolarize the cells. At rest, for a certain period of the time, maybe minus 60 millivolt can be achieved, and this is going to increase slowly. And when they are reaching the minus 40 millivolt, that's a threshold for the nodal tissue, the calcium influx occurs, and this action potential comes after the calcium channels are closed, inactivated, and the potassium channels is opening up and restoring the membrane potential to the rest. And again, this funny current comes, and this is repeatedly coming and depolarize the surrounding area. If we comparing the slope of this pacemaker potential to the SA, to the AV or the ventricle, we can say that the highest one in the SA node, slower in the AV node, and the slowest one in the ventricle. This is how the hierarchy works. The highest rate generated by the SA, slower can be generated by the AV, and the slowest one in the Purkinje. The action potential of the muscle cells and the connection to the contraction is pointed here in this graph. Here you can see this action potential of the muscle cells divided into 4 phases if we include the resting potential. Now the muscle cells has a resting potential around minus 90 millivolt. When it's depolarized, a fast sodium channel is opening up, and we do have a very fast peaking, and at the point of this peaking, the L-type calcium channels and the potassium, the rectifying potassium channels are opening up. This is why the action potential doesn't change too much and we achieve a plateau phase. And when the calcium channels are closing, only the potassium efflux works and restore the membrane potential to the rest. If you are looking at the contraction phase, this is usually is taking place by the end of this plateau phase. The absolute refractive period of the muscle cells is lasted from the depolarization till almost the end of this depolarization or end of the repolarization. When we are looking at the ECG tracings and the happening in the heart, we can see that the atrial depolarization is represented as a P wave on the ECG tracing. We do not have any sign of the sinus activity. Only the atrial depolarization can be seen on ECG. The next one, when the discharge goes through the AV junction, we see nothing. That's the isoelectric line, and that's the distance between the P and the QRS complex. When the bundle branches is going to activate the muscle cells, the ventricles, we do have the QRS complex. And when everything is depolarized again, we do have this ST segment when we do have this mechanical contraction. When the repolarization starts, we do have the T wave, and when everything is back to the normal, we do have the isoelectric line before the next cycle comes and before the next P is initiated. The 12 leads ECG placement. More than 100 years ago, when Einthoven attached electrode to the extremities, to the right arm, left arm, and right arm and the foot, and the left arm and the foot, this is how he could measure the bipolar leads such as lead number 1, lead number 2, lead number 3. Later on, when they wanted to have the absolute changes, Wilson and Goldberger introduced the limb leads. What they did, basically they connected the extremities to the very high resistance, and this is how they got a zero, absolute 0 point in the middle. However, this measurement could not give enough potential differences. So this is what they called VR, VF, VL. What they did to amplify the signal, they turned off the resistance, whichever arm was measured, and this way the absolute 0 millivolt was a little bit lower. And this augmentation that they achieved is about square root of 2 times was bigger than the original one. These kind of leads, these are unipolar leads because they are measuring the absolute changes comparing to a point. Now, the common one in these Einthoven leads and the Wilson and Goldberg leads, These leads are measuring the potential differences in the frontal panel, but they are not going to say anything about what will happen in the front and the back, so in the horizontal panel. This is why they attach some other unipolar leads to the chest, starting at the right side and goes all the way to the axillary area. 6 leads is placed in the chest, relatively cutting the heart in horizontally. Now, this way, in this 12 leads ECG, can be used very well to diagnose anything that's happening in the heart. The 12 leads ECG placement guide. We do have different colored electrode and different colored clips. A red one attached to the right arm, yellow one to the left arm, black to the right leg, and green to the left leg. Similarly to the chest leads, V1 red, V2 yellow, V3 green, V4 brown, V5 black, and V6 purple. This attachment, the chest leads, is starting in the fourth intercostal spaces and ended in the mid-axillary line on the same horizontal levels as V4 and V5. Now, if we summarize these chest leads, we will see that only in the anterior place we do have electrodes. We have no electrode on the posterior, on the back. This is why, in some case, in a special clinic, they are going to put further other 3 leads. It can be V7, V8, V9 as a continuation of the chest leads, or VD1, VD2, VD3 as a paravertebral dorsal leads. And sometimes, if we want to see the right ventricle, they are going to put another electrode toward the right side, and this is what they're measuring, V3R to V6R. They are the same position as a V3, V6, but on the right side. Electrocardiogram. We do have different waves. The atrial activation represented by a P wave. The normal P wave has a duration, it's about 0.1 second, and the amplitude is less than 0.25 millivolt. After the isoelectric line, we do have a Q wave. This is the first downward deflection after the P wave. We can have only one Q wave. The Q is the first negative wave in front of the first positive wave as an R wave. The R wave is the all positive deflection after the Q wave or after the P wave. So within the ventricle activation, every positive wave is called R wave. So we can have more than only one R wave. S wave is the negative deflection after the first R wave. So again, we can have more than only one S waves. D wave follows the QRS complex and represents the repolarization of the muscles. Terminology. This is very important because when we want to describe the shape of the QRS complex, we are going to use letters. And these letters is going to show or going to tell immediately how this ventricle activation looks like, what kind of complexes we are going to record. As you see here, this is a QRS. Small letters, so small cap represents a smaller deflection. A capital represents a bigger deflection. So this small q, big R, small s represents a small negative wave in front of the first R wave. The R represents a positive wave, and the S is the small negative wave after or behind the first R wave. In this case, we have no Q wave because the first R did not start it with a negative wave. So this is why this is an R, and because the next wave is a negative, this is RS complex. Here we do have again a small r, small s, and a second r, a big R wave. This is called RSR complex. Here we have only RS complex, and here again an RS complex. As you see here, the S is deeper one. This is why we do have a capital letter. That's a small Q wave, or here, if it's very deep one, usually they call as a QS complex. Another one, here we started with a Q and only R, there is no S wave. If the Q is deep, we can have a capital for the Q and a capital for the R as well. The activation of the ventricle, the normal activation of the ventricle. If we're looking at the chest leads, V1 usually represents the right side of the ventricle, while V6 represents the left ventricle. The first thing that is going to depolarize, this is the septum. The septum is activated from the left bundle. This is why we do have a left to right vector that pointing toward V1. This is why in V1 we do have an initial R wave, while in V6 we are going to detect a small Q wave. The next, when we do have an activation of the right and the left ventricle. However, because the left ventricle at least 2.5 times thicker than the right one, electric activity about 10 times higher than the right ventricle, mainly this is going to dominate the picture, so the vector is pointing to the left. This is represented in V1 as a deep S wave, while in V6 and a tall R wave. When everything is depolarized, we do get back to the isoelectric line. The third one, the final one, is a posterior area. However, this depolarization goes to the back, so relatively it doesn't give you any kind of changes in V1 or V6. If we are looking at the other leads from V1 to V6, you can see that the RS complex is transferred to the QR complex that it recorded in V6. What you do see, the R is getting bigger and bigger, while the S wave is getting smaller. Normally, the transitional point is between V3 and V4, when the R is bigger than an S wave. In this slide, you can see some intervals and segments that should be known very well. The intervals and the segments are different. The time duration is measured for intervals. The shape and the offset from baseline, elevation and depression is determined for segments. The interval that we call as a PR. The PR represents the AV conduction. This is started from the beginning of the P wave and lasts till the beginning of the QRS. If Q missing, of course, the beginning of the R wave. This is going to represent the atrioventricular conduction time that is in the range of 0.12 to 0.2 seconds. The QRS interval, this is from the beginning of the QRS till the end of the S wave. This is going to represent the duration of the ventricle depolarization that mostly is less than 0.11 second or 0.1 second. The QT interval that is ranging from the beginning of the Q wave till the end of the T wave. This is the duration of the electric activation of the ventricles or electric systole. Of course, it's going to depend on the frequency. This is why we should be correcting it. The correction of the QT corrected one, there's a QT interval divided by a square root of the RR, where the RR is in second. This corrected QT interval is less than 0.44 seconds.